Hello everyone, this is Mencho from Kyushu Institute of Technology. It is my pleasure to give you KiboCUBE Academy lectures about satellite testing. This is the content of today. I can list two references related to my lecture today. One is ISO standard. This is a testing standard specific to small satellite, including CubeSat. The standard lists the minimum set of tests you should do when you sell a satellite. If the satellite fails the test listed here, there is no possibility that the satellite will work in space. Another reference is a handbook recently published. I wrote a chapter of CubeSat assembly, integration testing, and verifications. This explains the detailed rationales of the requirement listed in ISO 19683, as well as general things about how to improve the satellite reliability. Before moving further, let me introduce myself. I have been working at the Kyushu Institute of Technology, QTech in short, since 2004, since 1996. Originally, my research area was spacecraft charging, but nowadays I'm more interested in lean satellites. It is another way of calling small satellite. These are the pictures of satellite I have been the principal investigator. Since 2012, so far, 19 satellites have been launched into space. Okay, let's talk about verification. Let me talk about what verification is. First, let's think about what do we do when we build a satellite. We first ask stakeholders, customers, users, what needs they have. It is called customer requirement. Please don't start building a satellite before you get the answer. Okay. Then we think about how the satellite solves the needs. It is called mission requirement. Then we define overall specification of the satellite to meet the mission requirement. It is called system requirement. Once it is done, we specify each component. It is component requirement. This is an example of GuaraniSat-1, which is the first satellite of Paraguay that was launched that was released to orbit in March 2021. The stakeholder requirement was to investigate habitat of insect carrying parasite. The mission requirement was to collect information of bug traps in remote villages from space. System requirement was receiving information from the field and forward it to the researcher. The component requirement was the transceivers capable of VHF uplink and UHF downlink. Requirement is imposed in upstream of the satellite development, and they must be met. Verification is a process to confirm whether the requirements are met or not. The process of defining requirement is from the top to the bottom, but the process of verification is from the bottom to top. We verify component first, then move to system verification, and lastly, we validate system against mission requirement. A different word and verification and validation are used here. Because even if the system is verified against requirement, which often utilize objective criteria, the final stage to confirm whether the systems can really satisfy the stakeholders, customers, user is based on subjective criteria. Then that process is distinguished from verification and called validation. Often we say the process to check whether the system is built right is verification. On the other hand, validation is a process to check whether the right system is built. Anyway, in this lecture, we focus on verification. When we build a satellite, you need to have a verification plan. The planning must start right from the start of the project. To plan the verification programs, you analyze the requirement and identify programmatic and cost drivers. The verification matrix is made. The matrix can be a table written in Excel sheet. You don't need any expensive software, just Excel sheet is fine. In the matrix, these items are listed. The last two items are rather important if you do not have access to testing facilities in your organizations, as those involve a lot of logistic issues. There are various methods of verifications. Test is only one of the verification methods. There are analysis, demonstrations, inspections, or even just document review. Demonstrations is similar to testing. It demonstrates whether items works or not. Examples can be seen in this YouTube videos. It shows antenna deployment demonstration. Okay, I do not play here, but you can watch this YouTube videos. Testing is not only the method of verifications. Then why do we test? Testing makes sure everything works accordingly before it gets into the field. I mean, orbit. Space system cannot fail because it is expensive and it is important, politically, socially, or military, or other reasons. Space systems is different from other systems, such as aircraft, automobile, electronics, because there is no chance of maintenance and repair. It is complex, production is limited. One important aspect of space system is that its system life cycle is really long. Sometimes a big satellite needs 5 to 10 years from mission definition to launch. Then it is difficult to accumulate personal experience in her career because you work only 30 to 40 years at most. If you are involved in 100 satellite project, perhaps you can make judgment whether we should do test or do differently based on your experience. Let's compare test and analysis. Test results are generally more credible than analysis results, but some tests are not practical. For example, it is very difficult to take into account combined effect of space environment, such as microgravity and vacuum. But at the same time, we cannot say that analysis is always cheaper, especially when you have to develop new software from scratch. After all, you should select based on optimization of the cost and schedules to obtain the best and adequate evidence. Also remember that the test and analysis are often complementary, such as case of thermal analysis and thermal test, structure analysis and mechanical test. When you develop a satellite, you go through various processes. First, you check the feasibility using breadboard models. Then you verify design using qualification models or engineering models. Then you verify flight models. You verify flight hardware and software using flight models. Qualification is a process to verify the design. We check whether the design is fully capable of meeting all the requirements. There is no need of using flight hardware, and over-testing is acceptable. Acceptance is a process to verify that flight hardware is free from any workmanship and material defect. We check whether the flight hardware has been built to the qualified design. One example of qualification, this is Hollywood 2. It is the first satellite at QTech. So far, we built 19 satellites, and this is really the number one, which went to space. Everything was new, especially the structure design. The satellite was originally designed as 3U CubeSat, but because of 25 years deorbit guidelines, we are required to increase the surface area. Design requirement for structure is that the structure shall have enough strength against mechanical load during the launch phase. We adopted this design. The design had to be verified before we make a flight model. Then we qualified by test and analysis. We built the test models and ran a series of vibration tests. We applied the test load with the margin. In addition, we ran analysis to show how far this structure can survive. In analysis, you can break the structure as many times as you want. Structure design was fixed after qualifications. Then flight hardware was built according to the design. And we need to check whether we build the hardware without any error. Human can always make an error. If you look at these pictures, the satellite is full of harness. You can easily make a mistake in connecting harness. The verification process is called acceptance. The method we adopted was test. We simply did a vibration test, but in this case, no margin was added to the test load. We just gave the maximum expected load. I now need to explain about margin. This is so-called power spectrum density of random vibration. The horizontal axis is the frequency of each accelerations satellite received during the launch. The vertical axis is the amplitude of vibration at each frequency. The higher the curve means the higher the stress is. Different color in here indicates measurement in different launch, although the rocket is the same. The shape of spectrums is different at each time. Then, when we do the test, we just take envelope of all the cases, which is given by this black line. We call this maximum predicted environment, and when we do the qualification, we give the load given by this red dashed line, which is higher than this maximum predicted level. The difference is the margin. We are giving more than expected. The picture shows the stress level and the probabilities. The blue is the probability of having a stress levels. For example, the vibration level during the launch or the temperature in orbit. Sometimes stress is low, sometimes stress is high. But overall, it stays within the levels with a certain probability distribution. The red is the probability of having system failure. Some system is very weak, then it fails when we apply this level of stress. Beyond these levels, no system can survive. There must be a gap between the maximum predicted environment and the lowest level of the system failure, so that no system failure occurs in an environment. Then the systems can survive the environment. When the blue and red overlap, if we are lucky, the environment is weak and the system can survive. or the system is strong and we can survive. But unfortunately, if the environment is strong and the system is weak, we may have a system failure. We have to avoid this one. The problem of space systems is that we don't have enough data to derive this red curve of the system failure probability. We don't know exactly where the lower limit of the system failure is located. Also, the environment has uncertainty. We have many data where the probability is high, but for the extreme case, the amount of data is not enough, like here. So we have this uncertainty. So we do the test at a level a little higher than the predicted levels by giving margin. Then we are sure at least the system is okay up to the qualification test levels, up to this one. Even if we have enough data of system failure probabilities, we still have a chance of extreme environment. After all, anything can happen in space. Then we test at the level higher than the predicted maximums to show that the system is okay, even if something unpredicted happens. That's the meaning of margin. So now let's look at the testing. Testing can be categorized into 3 types. One is functional test, one is measurement test, one is environment test. Functional test is to check the hardware and software work according to the requirement. It is similar to demonstration. The example shown here is end-to-end test. We check communication between the satellite flight models and the real ground station. Measurement test is to measure the some things and compare the measurement result to the requirement. The example here is antenna pattern measurement. We measure these radiation patterns of the antennas and check with the requirement of the antenna. In this case, for example, requirement is to have a certain level of the antenna gain, and we see whether the antenna gain is good enough or not. The environment test is to check whether the hardware can withstand the environment test. It involves inspection after the test, measurement before and after the test, and functional demonstration during the test. The example here is the thermal vacuum test. We confirm that the hardware can function at the minimum and the maximum temperatures. Minimum means coldest, maximum means hottest temperature in orbit. The example here is a thermal cycle endurance test. In this case, we don't need to operate during the test. Inspections and measurement or functionality check before and after the test are enough. We confirm that the hardware can survive a repeated cycle of hot and cold temperatures. This is a time, this is a temperature, so we repeat, in this case, minus 90 degrees, 90 degrees. So we repeat this kind of cycles many times. So this test is done usually for solar panels or antenna, some things that are exposed to the outer space, so that it has the largest temperatures differences. The example here is vibration test. In this case, we also don't need to operate a satellite during the test because it is for the launch environment. In the launch environment, small sat or CubeSat required to turn off the power. So that means it should not operate. So we confirm that the hardware can survive mechanical vibration during the launch through the inspection after the test and the measurement before and after the test. Here is a movie of the vibration. The example here is a shock test. The base plate where the satellite, in this case satellite inside the pod, is placed, it hit by a projectile, by air gun. We cannot see here, but we have an air gun here. And the air guns are launch a projectile. This projectile hit the table from the bottom. The impact to this base plate provides mechanical shock to the satellite. In this case, we don't need to operate the satellite during the test because the impact itself is very short, several milliseconds. We confirm that hardware can survive mechanical shock caused by the pilot devices on board the rocket. And we do inspection after test and measurement before and after the test. So, but please note, this test is not required for KiboCUBE because KiboCUBE is the ISS launch, ISS release, but for the rocket launch cases, you are required for this test. The example here is total ionization dose test. It is i.e. the radiation test. In this case, it is recommended to do functional demonstrations while the item is being radiated. We confirm that the hardware, mostly electronic part, can survive ionizing radiation for cumulative damages. There are various test models from BBM to FM. There is no clear definition of BBM, STM, EM, or QM. Different projects name the models in a different way. Anyway, these models do not fly. Proto-flight models and flight models, they fly. Okay. And these models also may exist also for the each component. Typical full approach of 1U CubeSat is the following. It is made of BBMs, EM, and FM. And for a typical approach of a very big satellite, EM is often skipped because some design experience accumulated. Also, building EM is expensive. But for 1U CubeSat, it's not so expensive to build EM. Also, for beginners, I strongly recommend to build EM because beginners do not have experience. And if you have enough experience, yes, you can combine EM and FM as prototype models and PFM. But for your first satellite, I strongly suggest you go through this process. So this is one of very frequently asked questions. How much should we do test before the launch? There is no clear answers. This equation gives how much satellite reliabilities decrease in time. This R is the probability that the satellite survives until time t from the launch without any failures. And in these equations, the lambda is a failure rate. It is the rate of failures occurrence per unit time. This failure rate decreases as you find defects in test and fix them. And the left figure of the bottom shows how the failure rate decreases in time as you do the testing. The more you test, this failure rate decreases, and the failure rate just after the launch is this one, decreases. Then the curve in orbit follows like this one. This red case is you tested only for short. This blue means you tested long time. And then the reliability when it was launched to the orbit, for case B, yes. It decays, but it is decays slowly compared to this case A. This is the data we obtained from our previous satellite project. I asked the project managers to count the number of problems during the assembly, integrations, and testing phase. You see that there are some jumps in the figure. This is when we start assembles, and when we move to thermal vacuums, the more you test, we can find more problems. Finding the problems in the test is good because we can still fix it. It is very similar to fixing a bug when you write a computer software. The more you test, however, the less new problems you find. You have to stop the test at some point. Otherwise, the satellite never goes to space. So when to stop? It is after finishing the minimum things you have to do. And the two references I gave at the beginning list the minimum things. If you have extra time until you hand over the satellite, you can continue until the last minutes to improve the reliability as much as possible. Now I explain what test we have to do, typically for 1U CubeSat. These are based on our experience when we deployed our CubeSat from ISS. First, electrical interface test, and you often buy components from the vendors. And after delivery, you check the component. Each component may work fine, but it may not work if they are connected. If there is any interference, if there is any interface mismatch, finding the cause involves lots of trial and errors works, which may take sometimes even more than a month. One thing to avoid is that you buy components from vendors, and if you buy components from vendors, you limit the vendors as much as possible. Buy from only single vendor. Ideally, yes, buy only from one. Then you can minimize the risk of interface mismatch. The next test is a functional test. It is make sure the satellite works in laboratory before you move to the environment test. If you don't do this and move to environment test prematurely and you find the problems, you cannot judge whether the satellite itself has the problems or the problems appears due to environment. The next test is EMC test and end-to-end simulation test. EMC means electromagnetic compatibilities. Okay. It is make sure your ground station can communicate with your satellite. You send command uplink from GS. Satellite does its job according to the command. You receive the data from the satellite at the ground station, and you do these processes by radio wave in air. Often electromagnetic noise inside the satellite may interfere with the satellite radio receiver. The signal from the ground decreases by many orders of magnitude when it arrives at the satellite. It can decrease by 10 to minus 14th orders of magnitude. Then the noise from the satellite may be stronger than the signal. Then you can never decode the signal. You can never decode the uplink command. Therefore, confirming the command uplink is really critical, and it has to be done as flight representative as possible. So no external power. Satellite is operated without any harness attached and completely free of anything, and operate battery and do the nominal operation. Next test is deployment test. Failure of antenna UHF or VHF deployment leads to DOA, which means dead on arrival. No radio coming, no radio uplink. So you need to make sure the antenna can be deployed in the worst condition. But at the same time, you need to make sure the antenna deployment timings complies with the safety requirement of the ISS release. It must be more than 30 minutes after the ISS release according to current interface requirement. The next test is launcher spacecraft interface test. For CubeSat, it is very simple. You just insert your CubeSat into the pod and confirm that it can fit smoothly. This is important as the structure may be skewed after full assemblies, which occurs very often even for one-year CubeSat. So you better do this before you deliver the satellite. Yes. The next test is thermal test. It is to check the satellite works in vacuums, hot temperatures, and cold temperatures. We also check that the satellite can survive hot-cold temperature cycles. We also do the mission simulations in flight representative environment, that is vacuum. This shows temperature distributions on PCB. This is vacuums, this is the atmosphere. You can see a hot spot occurring on the PCB. That's where the heat is dissipated. So in the vacuums, we have a risk of hot spot on PCB. Then things that work in atmosphere may not work in vacuum. Okay. So I strongly suggest you operate your satellite at least once in a vacuum, and so that even this one happens, your satellite can work. And not every people has access to a thermal vacuum chamber. In that case, I suggest you to check that the satellite works at hot temperatures, cold temperatures in atmosphere. One example to use this kind of industrial ovens, which is commercially available, but basically you can use any type of equipment as long as you can control the temperature. For cold temperatures, if you be careful about the moisture, you can use even refrigerators. Yes. So in addition to the temperature test, operate a satellite at least once inside the vacuum chamber, as I said before. You can use any type of chamber as long as it can make a vacuum environment. This is a very old vacuum chambers we bought at the second hand. So you can find this kind of chambers easily in the commercial market at very cheap prices, because already there are second-hand vacuum chambers supply. Because many of chambers are used in the semiconductor industry. When the semiconductor industry replace their equipment for their new generation of semiconductors, this second-hand vacuum chamber will come out to the market. So you can check it. Vibration test is required to check no loose bolt, no broken glass, no antenna deployment, no anomalies. There are two types. One is sign burst. To check against static acceleration. You can see motion at a very low. Another one, random vibration, check against high acceleration. Because frequency is very high, you cannot see its motion. Now, you may have these questions. Do we need to do radiation test? My recommendation is to try to mitigate the radiation effect by designing the satellite carefully. And because most likely you don't have access to radiation test facility in your country. Even in Japan, we are limited. Even if you want, you cannot. So think other way. One idea is to choose component parts that have flight heritage. When you buy a component, you should ask the vendor. And make sure that you can finish a mission objective in a short time, such as several months, before your electronic parts degrade. You should not expect that cause commercial off-the-shelf electronics parts to last a long time, such as longer than 3 years in orbit. But in another word, many quartz parts can last for 3 years in low Earth orbit. Also, design the satellite to recover from malfunction due to single events. You should design so that you can turn off and turn on if the satellite is hung up. It is the same way as you do for the computer. When it hung up, you just turn off the power and turn on again. And please remember that many CubeSats works in orbit without doing radiation test. Finally, conclusion. Please remember that building a satellite is not your purpose, and the satellite must work in orbit after all. Testing will improve the odds of mission success, and do not overtest, however, but do all the tests you have to do. Thank you.